Hello teachers, and welcome back to Chapter 4, Section 4-2. This is the second part of the video, and we're talking about prime factorization, prime numbers, composite numbers. And I want to start off with a question. How many positive divisors does 24 have? Notice it says we are not asking how many prime divisors, so this is not prime factorization, just the number of divisors. This is any divisors. All right, so since 1 is a divisor of 24, then 24 divided by 1 equals 24 is a divisor of 24. Notice they connect up in this picture, the 1 and the 24. Remember the pairs we talked about earlier when we were listing the number of divisors? They show up in pairs unless you have a perfect square, and then you'll have an odd number of divisors. So 2 and 12 go together because they multiply to be 24. 3 and 8 go together because they multiply to be 24, and so do 4 and 6. So all of these are divisors: 1, 2, 3, 4, 6, 8, 12, 24. Again, not prime factorization. These are just divisors of 24. How many do we have? We notice we have 1, 2, 3, 4, 5, 6, 7, 8 divisors of 24. Now, another way to think about the number of divisors, and by the way, we decided, let's remind ourselves, how many divisors do we calculate on the other page? I'm counting 1, 2, 3, 4, 5, 6, 7, 8. So 24 has 8 divisors. Let's write that at the top. So 24, we counted them, has 8 divisors. Now, another way we could take a look at that is look at the prime factorization of 24. So you remember when you do the factor tree or you do the repeated box method to find prime factorization. So we can look at each of the factors. So 2 to the third right here, that's equal to 8, right? 2 times 2 times 2. 8 has 4 divisors. We could list them. It's 1, 2, 4, and 8. Times 3. Separately, how many divisors does 3 have? Just 2. Now, from the fundamental counting principle, we can calculate how many divisors 24 will have by counting these 4 times these 2. So 4 times 2, that's every possible combination. 4 times 2 is equal to 8 divisors of 24. Now, what the chart does below is actually list the divisors, and when I was talking about combining these every way possible, so you could combine together, what they're saying is 1 times 1 will give you the divisor 1, 1 times 3 gives you the divisor 3, 2 times 1 gives you the divisor 2, 2 times 3 gives you the divisor 6, 4 times 1 gives you the divisor of 4, 4 times 3 gives you the divisor 12, and finally, 8 times 1 gives you the divisor 8, and 8 times 3 gives you the divisor 24. This chart I find a little bit more confusing, but that's the same idea. You'll see them listed at the bottom: 1, 2, 4, 8, 3, 6, 12, 24. So that's all 8 divisors. Remember, 1, 2, 3, 4, 5, 6, 7, 8, and down here you also see 8 divisors. Now this is a fun property here. If P and Q are different primes, so for instance, for 24, we had 2 to the third times 3. The 2 would be the P, and then the 3 would be the Q. Our different primes, M and N, are whole numbers. M and N are our exponents. Then we can say, due to the fundamental counting principle, that N plus 1, again, the exponent plus 1 here, times the exponent plus 1 here, whole number divisors. That's how many divisors you would have. So for the previous page, remember when we had 2 to the third times 3 to the first, we ended up multiplying, this would be 3 plus 1, which was the 4 we talked about, times 1 plus 1, which was the 2 divisors we talked about, or 4 times 2 equals 8 divisors. And recall this was for the number 24. So if you have it factored completely in prime factorization and you have it written in exponent form, add 1 to each of those exponents, use the fundamental counting principle to multiply those together. And that's how many divisors, not just prime, but how many divisors your number has. So we're going to try to find the number of positive divisors of 1 million. How could we do this? The number of positive divisors for 1 million. Now, if we use the rule that we just learned, if we could break this down into prime factorization, we could use that trick where we add 1 to each of the exponents and then use the fundamental counting principle to multiply them together. So let's do this by hand, and then we'll look at the typed version so you get to see it twice. 1 million, you know that is going to be 10. Let's get my pen working. 10 to what power? 10 to, you know it's got 1, 2, 3, 4, 5, 6 zeros, right? So 10 to the 6th power. How could I do that quickly? Now, there's nothing wrong with a factor tree or the repeated box method here, but I'm saving you just a minute because again, with all those zeros, I know that's just 10 to the 6th power. 10 I can write as 2 times 5 to the 6th power, correct? Which is equivalent to 2 to the 6th times 5 to the 6th. That's a property of exponents. Then we can use the fundamental counting principle to figure out the number of divisors, not prime factors, but just plain old divisors, is going to be 6 plus 1 from here, and then 6 plus 1 from here, which is 7 times 7, which is 49. Now remember something that we didn't prove, but we decided that anytime you have an odd number of divisors, that number was a perfect square. And this is definitely a perfect square. A million is what? 1,000 times 1,000. Now let's revisit this with the typed up version. Okay, so the prime factorization of 1 million is, and they just jumped right in there, but they did do it the way we handled it. They wrote that as 10 to the 6th. Again, any number with all those zeros is just going to be the 10, and then you count the zeros there, okay? Or any one with all the zeros. Let me be very specific. A 1 with zeros is going to be 10 to how many number of zeros you have. The 10 breaks down into 2 times 5. That's 2 to the 6th times 5 to the 6th. And then 2 to the 6th, remember, has 6 plus 1 equals 7 divisors. The 5 to the 6th also has 6 plus 1 equals 7 divisors. And then using the fundamental counting principle, you could say 7 times 7 is 49 divisors. And again, informally, we talked about anytime you have an odd number of divisors, you're dealing with a perfect square. All right, find the number of positive divisors of 210 to the 10th power. So you don't want to do a factor tree for this. It's enormous. Type that in your calculator and see how big that thing is. Let's see if we can handle it like we did just a minute ago. So I'm going to start with 210 to the 10th power. Now, what's another way I could write 210, right? So that's going to be, how about 3 times 70 to the 10th power? The 70 is not prime factored right now, so I could say it's 3 times 7 times 10 to the 10th power. I'm going to keep going. 10 is what? 2 times 5. So 3 times 7 times 2 times 5 to the 10th power. And it sure would look a lot better if this was in numerical order, right? Ascending order, 2 times 3 times 5 times 7 to the 10th power. And then each one of these guys is raised to the 10th power. And what we have here, y'all, is the prime factorization of 210 to the 10th power. Now, how many divisors are we going to have? Remember the rule, we add 1 to the exponents. So 10 plus 1 is going to be 11 for the 2. The 3 is also going to have 11 divisors. The 5 to the 10th is also going to have 11 divisors, and the 7 to the 10th is going to have 11 divisors. So this is 11 to the 4th divisors, y'all. That is a bunch of divisors. Is that an odd number or an even number by chance? Well, 11 times 11 times 11 times 11. Remember we talked about if we multiply all odd numbers, you get an odd number. And if you have an odd number of divisors, you're dealing with a perfect square, right? So that means 210 to the 10th power is a perfect square, which would really be 210 to the 5th times 210 to the 5th without actually calculating it. Now let's see how this is typed up, and even the textbook version of this, they might multiply that 11 to the 4th hour out. We'll find out. So what do we do? The prime factorization of 2 to the 10th to the 10th. 210 to the 10th, can't even say it properly. They broke it down to 21 times 10. Is that okay? Sure. That's equal to 210. Then 21 they broke down into 3 times 7, and 10 is 2 times 5. And they went ahead and organized it, which means each one of those prime numbers is raised to the 10th power. Because anytime you have a product raised to an exponent, that means each one of those factors is raised to that exponent. Then you add 1 to all the exponents, and that would be 11 times 11 times 11 times 11, or 11 to the 4th. Notice they did multiply that out for us, and we have an odd number of divisors, but it's a big number, 14,641 divisors. Would you like to list all those? Whew, no, you certainly wouldn't. All right, to determine if a number is prime, you must check only divisibility by prime numbers less than the given number. As you can imagine, if you're trying to figure out if 103 is prime, there would be no need to go past the prime number 103 or the number 103 to find a prime bigger than that. It's not going to divide 103. So, for example, to determine if 97 is prime, we must try dividing 97 by the prime numbers 2, 3, 5, and so on, as long as the prime is less than 97. But as you can imagine, and I'm not reading right now, as you can imagine, you wouldn't really even have to go that close to 97. How close would you actually have to get? Be thinking about that. If none of these prime numbers divided 97, then 97 is prime. Upon checking, we determine that 2, 3, 5, 7, they do not divide 97. So they just checked. We know 2 doesn't, right? Because 97 is not an even number. 3 doesn't, because 9 plus 7 is 16, and 3 doesn't divide 16, therefore 3 doesn't divide 97. 5 doesn't divide 97. Why? Because it doesn't end in a 0 or a 5. And 7 doesn't divide 97 because we just divided, and it didn't work. And here's a challenging argument, but here we go. Assume that P is a prime greater than 7. Remember, we've checked all the primes through 7. So just P is some prime bigger than 7. And P divides 97. So we're saying there's some prime number that divides 97 that's bigger than 7. Then we also know that 97 divided by P also divides 97. Remember when you have divisors. So for instance, if we know 6 times 3 is equal to 18. Okay, don't worry about prime right now. Just 6 times 3 equals 18. Then if you divide 18 by 6, you get 3. And it works the other way also. If you divide 18 by 3, that gives you 6. That's what this is saying. So if P divides 97, then we also know that the number 97 divided by P also divides 97. Okay, so just hang with me. They both, it's just like 6 times 3 is 18. They both divide 18. So if I know 6 divides 18, then 18 divided by 6, which is equal to 3, also divides 18. Okay, I'm going to get rid of this because it's kind of in the way. That's just so we can talk. Now, keep hanging with me. Because P is greater than or equal to 11. Why do we know that? Because 11 is the next prime number after 7. So I know that because that prime number is bigger than 7, that your prime number P has to be greater than or equal to 11. Okay, that means that 97 divided by P, so when you take 97 and you divide it by 11 or something even bigger, then your answer is going to be less than 10. Right? But that's a contradiction because we found all the prime numbers less than 10. We checked them all and none of them divided by 97. What does that mean? Well, if n is composite, then wait, we didn't finish. What does that mean? That means p is prime, okay? So I know where the last of that page went, but that means p is prime. The page that we have here really kind of summarizes that example, and this is the official rule. So if n is a composite number, then n has a prime factor p such that p squared is less than or equal to n. And it really comes from that example of 97 that we did just a minute ago. Now, what are we supposed to get out of this story? Because I know that example could be a little bit on the confusing side. We know that we are supposed to check the prime numbers all the way to the square root of n. That's really the best way to think about it. So, for instance, if we go back to the example of 97, is 97 prime? Okay. Now, if you're looking for, like, the square root of 97 would be a nice way to do it, or the perfect square, just lower than 97. But I could even type in my calculator the square root of 97. Now, I've told you to kind of stay away from your calculator, but it sure would come in handy right now. And when I type that in my calculator, the square root of 97, it gives me 9.8, which rounds up to 10. Now, the square root of 97 is obviously not 10, but if I check the prime numbers all the way up, that's supposed to be the square root of 97. If I check the prime numbers all the way up to that value, and they are 2, 3, 5, 7, the next one's 11, right? I don't even have to check 11, because 11 is the bigger than the square root of 97. And if all those values do not divide 97, know that 97 is prime. Okay, so hopefully you will find some value with that. So is 397, is that composite or is that prime? And so we need to just start checking our values. Now, one thing you want to know maybe before you even get started is how many numbers do you have to check? And so again, a quick way to handle this is to take the square root of 397, get a rough idea of how big that is, and then check your prime numbers up to that value. And so the square root of 397 is approximately 19.92. So if we check our prime numbers up to that point and none of them divide 397, then we know that 397 is prime. So I'm going to check 2, 3, 5, 7, 11, 13, 17, 19. And if I don't find anything on that list, then I know 397 is prime. Okay, so let's just start checking. And here's what we have. The possible primes, look, they've got them listed for us. This is exactly what we did, right? Okay, because none of the primes, 2, 3, 5, 7, 11, 13, 17, and 19, divide 397. We know that 397 is prime. Now, how could we quickly tell whether these numbers divide? Well, first of all, you know why 2 is off the list, because this is not an even number. 3, we add the digits. 3 plus 9 is 12, plus 7 is 19. And 3 doesn't divide 19, so it's off the list. Why is 5 off the list? Because the units is not a 0 or a 5. 7, you'd have to do the old way, right? And they tell us that 7 doesn't divide. 11, you know the trick where you add every other digit and then subtract the opposite every other add. So 7 plus 3 is 10. 10 minus 9 is 1. 11 doesn't divide 1, so 11's off. 13, old way, folks. 17, old way. None of those divided, therefore 397 is prime. Let's do another one. Hey, why don't you try to pause this one? Remember, the approach is to take the square root of 91 or figure out what number squared gets you just over 91. That's the best way to think about it. And check your primes up to that point. Once you find one, then you know it's composite. If you do not find a prime up to that point, you know it is prime. All right, how'd it go? So square root, come on pen, square root of 91, about how big is that? Again, I don't mind a calculator on this. So square root 91, it's approximately 9.5. Now listen, a smarter way to think about that is 100's bigger, right? The square root of 100 is 10. So, if you go up to 10 in primes, 10 is not a prime, then you're completely safe. So you could round up to the nearest perfect square past 91 and knock this out without a calculator. That's probably the way I need to be thinking about it and the way to talk to you about it. So what are the primes up to 10? Well, again, 2, 3, 5, 7. After that's 11. We don't even have to check 11. Now, does 2 divide 91? You would say, nope, it does not, right? Because 91 is an odd number. You're looking at the ones place. Does 3 divide 91? And you say, no, it does not, because 9 plus 1 is equal to 10, and 3 doesn't divide 10, so 3 doesn't divide 91. 3's out. Does 5 divide 91? Absolutely not, right? Because the 1 does not end in a 0 or a 5, so the 5 is out. And does 7 divide 91? There is a divisibility test for 7, but I think it's uber complicated. It's easier to divide by 7. So let's do it. 7 divides into 9 using your standard division algorithm. It divides 1. So 1 times 7, is 7. Subtract 2, bring down that 1, correct? 7 divides 21 3 times. 3 times 7 is 21. Look at there. We got a remainder of 0. What does that mean? That means 7 divides 91. If 7 divides 91, that means this number is composite and not prime. Now, I'm pretty sure I've got a typed up version of this for you, but if not, you've got it. Let's see. The possible primes, here we go, are 2, 3, 5, and 7. We check them all. Turns out 7 works out. I've got something really cool for you. It's called the sieve of Eratosthenes. It says one way to find all the primes less than a given number is to use the sieve of Eratosthenes. If all the whole numbers greater than 1 are considered or placed in the sieve, the numbers that are not prime are methodically crossed out or dropped through the holes of the sieve. They're telling you why they describe it this way. The remaining numbers are prime. A little bit about Eratosthenes. He was a Greek mathematician that lived 276 to 195 BC. In other words, a really long time ago. He was a mathematician, geographer, poet, astronomer, and music theorist. He is known for calculating the circumference of the Earth and developing geography. Longitude and latitude, I do believe, is based on the work of Eratosthenes. But he came up with this really cool sieve. So in terms of math, this is what we're talking about. So notice I've got all the numbers written to 100. You're going to have a homework problem, I think, that you may want to do this all the way to 120 because you need a visual list of all the prime numbers between 1 and 120. So my advice is to just do this on your paper. It's very rewarding. You could even extend this to 120 if you want to, but I'm going to show you the trick. Here's what we're going to do. First of all, I'm going to make my pen just a little bit wider so I can see it better. Any number that is divisible by 2, that's where I'm going to start crossing it off. So the first prime number is 2, right? Any even number is divisible by 2. Look, everybody in this column is completely marked out. So these guys are going to fall through the sieve. Look, the next column is all odd numbers, so they don't get marked out. Not yet. But all these even numbers, once again, are marked out. Everything under the 6, 36, 46, 56, 66, 76, 86, 96, completely gone. Everything is gone that has an 8 in the ones place. And then look, all these zeros are gone as well. Why? Because all of these numbers are divisible by 2. Okay? Now the next thing I'm going to look at numbers that are divisible by 3, but it's not quite as fast to mark them out. Okay, now 3 is prime. I don't want to mark through 3. And you know what? I accidentally marked through 2. I don't want to do that, right? Because I know 2 and 3 are prime. Matter of fact, let's just circle them now so I don't do something silly. 5's prime, 7's prime. Okay, 9 is not. We'll get there in a minute. But numbers that are divisible by 3, you can count 3. In other words, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Notice I've got some of these already marked out. 1, 2, 3, 1, 2, 18 is divisible by 3, 1, 2, 21 is divisible by 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Now I'm going to pause it. I'm going to do this all the way down. I want you to pause it and imagine how you would do this, or either set this up on your own paper right now. Okay? I didn't notice this. I think I accidentally marked through 32 as a 1, 2, 3, but it should be 33. Careful with the counting. But again, I'm going to mark out all the divisible by 3's by counting 1, 2, 3. Look, I'm at 33, right? 1, 2, 36 is the next one. I'm supposed to be doing this in pink. Hold on. Okay, so 36 was the next one. 3, 1, 2, 39 is out. 1, 2, 42 is out. 1, 2, 45 is out. Again, so you don't have to hear me do this. I'm going to pause it and come back with that done. Okay, I'm back. Except my seed disappeared. There we go. Okay, I'm back. Now, I'm going to pick a different color. The colors don't matter, honestly. Not at all. Pencil's fine. So I've looked at all. I've marked out everything divisible by 2. I marked out everything divisible by 3 by just counting to 3. Okay, now I'm going to mark out everything divisible by 5. Now that's easy, right? Anything that ends in a 5 or a 0. So I've already got some stuff marked out here. Okay, but the 25, the 35, the 55, 65, 85, and 95, those can go. But look, everything that ends in a 0 was already marked out because we did that for even numbers. I've handled my 5s. Let's handle our 7s, right? So 7 is about like 3, y'all. It's not fun. So just hang with me. I'm going to change colors again. What can we do? Blue. All right, so I'm going to count to 7. So I'm at 7. Don't count that. 1, 2, 3, 4, 5, 6, 14 gets marked out. 1, 2, 3, 4, 5, 6, 21 gets marked out. Or you can look at all the multiples of 7. You know, 3 times 7 is 21. 4 times 7 is 28. 5 times 7 is 35. 6 times 7 is 42. So far, they're all marked out. 7 times 7 is 49. There's a new one. 8 times 7 is 56. 9 times 7 is 63. 10 times 7 is 70. It was already marked out. 11 times 7, hey, that's a new one. It's 77. 12 times 7 is 84. It was already marked out. And then 13 times 7 is already bigger. I lied. 13 times 7 is 91, so it gets marked out as well. Now, had I been just counting by 7s, I wouldn't have run into that issue. So there's an advantage for counting by 7s. Now, do we have to go any further? So that's the question, right? Remember, we're going to 100 right now. So the square root of 100 is 10. So I don't have to check any prime numbers larger than 10, and 7 is it. That's as big as it gets. The next prime number is 11. Now, if you draw this out to 120, you're going to have to check numbers. Are you going to have to check numbers divisible by 11? What's the square root of 120? Is that bigger than 11? You know, 11 times 11 is 121. So you do need to check through 11 when you take this out to 120. Now, let's circle the prime numbers. So I've got 2, 3, 5, 7. Remember, 1 is neither prime nor composite, so it's not circled. Circling these guys in pink because they'll be easy to spot. The next number is 11. We knew that. 13, 17, 19, 29 is the next one. 31, 37. Oh, I skipped 23. I knew there's another one in the 20s. 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89, 97. So it seems like there are no steadfast rules about these prime numbers, right? Now, I've got another page for you that you might like better than mine, but it looks very, very similar. The sieve was created exactly the same way, but completed. And hopefully, all the prime numbers that I have listed match. Look, there's 3 of them in the 70s, 2 of them in the 80s, but only 1 in the 90s. There's 2 in the 60s, 2 in the 50s, 3 in the 40s, 2 in the 30s. So, you know, it's hard to find a pattern. Now, I'm at my 30-minute mark, so what I want to do is shut this video down. And really, that's the last topic that I wanted to cover. But I've got like 3, maybe even 4 homework examples that I would like to work with you, because the homework can be a little bit confusing. As you already know, some of these problems are very challenging. And so there's a few that I just want to look at together. So part 3 is going to be looking at some homework examples.